Right. So this is pretty easy, pretty straightforward because you have learned software in IT as well. So nothing much here. So let's get going, right? Basically, when you have software, they can be divided into two types. It's system software and application software. And system software are needed to operate the computer, while application software are used to uh, perform our day-to-day tasks. I hope all of you can hear me.
Yes, sir.
Ima, can you hear me?
Yes, sir.
Okay, great. So what are the two types of software? You have application and system, right? Application software and the system software. And when you take a system software, they can be divided into two categories, actually three. Here they have given only two. That's the operating system, which is the main system software, and then the utility software. Utility software are the supportive software. Support the OS. You can write this in your book. You can highlight, write utility. That's why it's called utility. And the other, which is not here, is translators. Translators. Now, translators' job is to convert program code into machine code. When you write a program using a programming language, it needs to be converted into machine code in order for the computer to execute. So that is done by translators. So translators, utilities, and operating systems are all coming under system software. And application software, of course, word processing, spreadsheets, database, and so on. You have so many types of application software. Okay. So while you are listening to me, while you are watching this, you highlight your book and then write these things in your book, right? Okay. Operating system, as you know, it's the main system software, and we need a platform to work. So that is provided by the operating system. Operating systems, now we have different types of devices apart from computers. Computers, of course, need an operating system, but when you take an embedded system, embedded device, you can't really call it an operating system. It's basically a set of instructions written into microchips or ICs, which will be executed when the power is given. And we call them firmware. When the instructions are written into ROM chips, they're called firmware. So embedded systems, they run on firmware, while computers, smart device, computers, PCs, they run on operating system, but they also have firmware at the startup of the computer. We'll talk about that later on. Software written for general purpose computers need to be able to run on a range of different hardware. So operating system's job is to perform the management, controlling of hardware in the computer, and also to provide an interface between us and the hardware. For example, if I want to access the hard drive, I need to go to the Explorer. And Explorer is a program running in the operating system. Your favorite web browser runs on your laptop or desktop computer, also needs your mobile phone or tablet. One of those jobs of an operating system is to manage whatever input and output devices the computer has. So apart from providing an interface, it does much more. Much more. Like managing the resources, right? So general purpose computer does many jobs, whereas embedded systems, they can perform only a set of limited tasks. Embedded systems, uh, limited tasks. This one, general purpose, range of jobs. So they are going to handle many hardware, different types of hardware. One of the jobs of an operating system is to manage whatever the input and output devices the computer has. So it manages input devices, output devices. It manages resources, right? It provides an interface, right? This interface uh, between the use and the hardware. Right. When it comes to resources, what are the resources it manages? Well, it manages the storage. It manages the RAM. It manages the CPU time. We'll talk about them. And it manages the hardware as well. I mean, input output devices, I/O devices. Okay. A programmer writing an application uses simple commands, open file, and the operating system deals with exactly how to open this file. So that's okay. Can you tell me, like, we just need to write open file, and the operating system deals with exactly how to open the file. So I don't need to worry about how to open the file. What do you call this concept? When I use the command open file, operating system deals with how it should be done. I just need to run the command. What do you call this concept? We have learned that. Anyone? Hello? What do you call that concept? Where we don't have to worry about how things are.
So is it abstraction?
Exactly, that's abstraction. Yes, good. Right, that's abstraction. So the operating system will interpret how it should be done. We just need to concentrate on how to use the command. Abstraction. This will depend on what sort of secondary storage of the file has to be open. You might have realized this. This is another. It's there. It's here. Yeah. Nobody saw this. Right. That's abstraction, and there are levels of abstraction. Right. This system means application have to be written for a particular operating system, but will work on any hardware. Right. And hardware devices, they come from different vendors, right? Different manufacturers. So still the operating system must be able to recognize that hardware and deal with it. And that's where this hardware comes with another system software actually. There is another one. This hardware that you plug or the peripheral devices, they come with another system software which is called drivers. Drivers. So these drivers are written to communicate with the operating system. So that's why when you buy a printer, you just need to plug it and automatically the drivers are downloaded or taken from the OS itself, and the OS starts to recognize the printer. And the OS is Windows and the printer is from HP, and they talk to each other with the help of the driver. Back then, we had to install drivers using CDs. And if you lost the CD, there was no way to find the driver. But now we can download, and in fact, we don't need to do anything. There's another level of abstraction there. We just need to plug, that's all. And the OS will does the rest. Identifying the device, downloading the driver, right? That Android apps run on any Android device. Many different models of smartphone tablet will run on app, but the same app won't run on your friend's iOS. So sometimes you see certain software applications which are developed on a particular platform runs only on that platform. That's why you need an Android app as well as an iOS app of the same product. That's why they develop two versions. So platform to platform, the software may run differently, but operating system tries to make a common ground for all the hardware and software, so that it runs on. It runs most of the applications and most of the it controls most of the hardware, recognizes. Highlight and write. Okay, so this is the overall picture. You have the operating system, underline you have the hardware, and on top you have application software. You have utilities, web browser, image editor, word processor, they all are application. Utility is a system software, but most of the utilities are bundled with the operating system, or you can even run as separate applications, third-party applications, right? For example, McAfee is a utility that bundles with the operating system, Windows. If you install any other antivirus software, that will be a third-party antivirus software. So can have both versions. Operating system provides developers of application programs like word process, a set of commands such as open file, display, JPEG. This set of commands is usually called application programming interface. Now, how many of you have heard about this term API? API? Anyone?
So I've heard of it, but I haven't like
Uh-huh.
known much about it.
Okay, right. Some developers, they write APIs also. They write. So API is something like it's something like this. Uh, let's say you have a software, right? You have a software, and there's another software developed by another, let's say your friend. Now he wants to integrate this software into your one, not completely, but he wants to create kind of a mm, mutual link between the two, so that this software will recognize certain commands sent from this software, right? So if this software wants to combine with this one or talk to this one, uh, it should know how this software was written and what kind of command set that this software deals with, right? So that is the part which is called API. So this guy who writes the documentation of this software will have written about the API and the commands and everything. And if someone wants to develop a software that could communicate with this one, he has to go through the API documentation and write the code into that. So after that, the software will talk to this one, and you can combine the two. We can work with the two. So that's the whole idea, right? Operating system provides developers of application programs like word process with set of commands, open file, display, JPEG. This set of commands is usually called application programming interface, API. Using the operating system API rather than accessing hardware directly means that application program will run on the operating system, right? So the operating system will handle the hardware. If you write a software to run on that OS, you just need to develop your software to be in line with the API of that operating system. You don't need to like You don't need to access the hardware directly. OS will do it. You need to talk to the OS, who will deal with the hardware. That's what it means. It doesn't matter what hardware it is installed on. It also means that the operating system controls what application programs are allowed to do. This helps to reduce the risk of programs crashing, to maintain the and also to maintain the security. That means there are numerous application software running, right? And then you have hardware. You don't allow these software to access the hardware directly. Instead, the OS will do it, right? So the software has to be designed to talk to the OS, right, with the help of API of the OS, and the OS will deal with the hardware. So the OS will manage who is accessing the resources, and it will control the software here. And also, it doesn't allow the software to access the hardware directly. Therefore, there's security as well, and it avoids crashing. Right? Imagine one software is holding to a particular hardware throughout, right? Just like you guys, right? or people who will hold into something like they don't let other people use it. But OS does not do that. Like it will control, right? If this software is done with the work, it will give the chance to them. Right. That also it doesn't wait until the job is completely done. Right. It'll do up to some extent and then switch to the other. We'll talk about that in a moment. Right. In general, managing files and the directory structure and input output is one of the important, right? Okay. So here's another function of operating system, right? So although they haven't really list down all the functions, they have described it in these paragraphs, right? So that's why it's important to highlight managing files. So the OS will do managing of files, directory structure, how the folders are created, how the files are dealt with, managing files and directory structure, and input output, right? So here are two jobs. One is this, and here's another one. Input output, we can say input output control. That means it's controlling the input devices and the output devices when reading and outputting information, reading data and outputting information. An operating system also shares access to hardware among different programs. That means it can share hardware. Some operating systems among different users who are logged onto the computer. Some operating system will share the hardware among different users. Not only different programs, but on different users as well. Two important pieces of hardware that have to be shared are the CPU and the RAM. Well, hardware sharing can be like sharing the print also, but what about these two? Two very important is actually resources, hardware resources. Two important resources that the operating system will share among the programs are CPU and RAM. CPU and RAM. In the chapter on hardware, you learned on the von Neumann architecture. So one group didn't do von Neumann and hardware, so I'll be doing that again. We'll talk about that. The operating system keeps up this illusion by allowing each program to use the CPU for a short time. That's what I was telling you, right? When there are several processors, right? when there are several processes running, right? Now, what is a process? Can anyone tell me what is a process? Process. What's the difference between the program and the process? Yeah.
So program is a set of instructions and a process is inputting something and modifying it to get an output.
Actually, Atma, it's process is a program which is running, which is being executed right now. Okay, that's what you see when you go to Task Manager. You see all the processes running right now. So Word is installed here, but when I click on Word, it starts as a process. When a process is started, we need to allocate CPU time for that process, right? We need to allocate RAM. Why do you need RAM? Because the process will be running on RAM. Now, as a multi-user, as a multitasking system, we don't run only one process and we don't close it to run the next process. These processes are run in parallel, right? And if the CPU is having multi-cores, these cores can handle different processes at the same time, having true parallel concept. But if not, the CPU time is precious. So the CPU time has to be allocated among these processes in a controlled manner, right? In a controlled manner, because it's a resource. If it is a resource, other people are also waiting. Other processes are also waiting. Just like the RAM. So who is doing this? It is the OS who is handling the CPU time among these processes. How does it do it? It does it by something called scheduling. Scheduling. So as the name implies, scheduling means allocating. It allocates the CPU time among the processors based on a priority in a priority basis, right? It will look at which process needs the CPU and the RAM, CPU time and the RAM, and allocates it. And then it doesn't let that process hold onto the CPU time and the RAM throughout. What does it do? Right? It will switch that to another process. Give it up to some extent and then switch to the other. And then later it will come back to the previous process. Right now, for example, let's say there's a process running. At a certain instruction, the process should wait for an input from the user. User has to input some data, let's say adding two numbers. So in that stage, it has to wait. Will the CPU wait? No. CPU will switch its service to another process. And later, when the user enters the data, it will come back to that previous process. But there should be someone who's handling the CPU, and that is OS. It is a job of the OS to do that. Okay. So now this concept is really a nice concept, scheduling. You know, I am using this concept in my day-to-day work, which means when I'm working, I don't try to complete one task until the end. I do it up to some extent. And then I will keep a record where I stop that and then switch to another task. I will do the same thing with that task and then move to another one. And later I will come back to that previous task and, continue again in the same manner. Right? This is a fantastic concept. You also try will even when you are studying. Right? We tend to study. I have heard you guys saying, today I will finish IT. Tomorrow I will take maths and complete. I wonder that works. So rather try scheduling. If you are the CPU, try scheduling your CPU and other resources, and do it in a time sharing basis. I think it will work really well. And because when you're holding into one task throughout, it becomes boring and it doesn't really work, right? And when you're holding one subject, when you're trying to complete studying one subject, the other subjects are waiting for you. How not, right? So try scheduling, implement this. So computer science allows us to implement a lot of things in our day-to-day life, right? Try that. It's really, really interesting. It is possible to load many applications at all the same time, and each uses some memory. So RAM, RAM, right? RAM is the working memory. It's like your desk where you keep your books and study. So RAM is the working memory. Working memory. Secondary storage is not the working memory. It's the RAM which is the working memory. So everything is loaded into RAM when it is being executed. Right. But then there's a problem, right? You have learned this in IT. Sometimes if your RAM is not enough, what will happen? Your RAM will run out. What if you keep loading applications until RAM is full, right? You're trying to overload the computer with many applications without knowing that you have only 1 GB RAM or 2 GB RAM. What will happen? RAM will run out. It's like your desk is full of books. Now there's no space to keep more books. What happens? What should you do? Right? It can lead to a crash. So to avoid this, what you do is you move some of the program and data out of the RAM, to where? To a disk. Now disk is secondary storage. Disk is secondary storage, HDD or SSD. So you move some of the data and files, instructions from RAM to the secondary storage. You borrow a certain space from the secondary storage, right? So there you borrow. This space that you borrow from the secondary storage is known as what? What do you call it? What do you call it? What do you call
The
this?
VRAM.
Yes, that's the VM, virtual memory. You borrow this virtual memory from the hard disk drive or the SSD, right? This can be SSD also. And then what you do is some of the data that you have in RAM will be moved to the VM and brought back. So this is swap out and this is swap in. You swap out and swap in. When do you bring it back? When the RAM is vacant, when certain processes have been terminated and the RAM is vacant, you bring back those data from the VM to the RAM. So it's something like this. Your desk is full of books. Now you look at, you need more space because you need to keep some more books. And then you see some books haven't been used for a while. What you do is you move them to a nearby shelf or something. And then when the desk is a little bit empty, you bring that book from the shelf and keep it on the table. Something like that. Okay. So moving this data and instruction back and forth is called swapping, or it's also called paging or swapping. Okay, and where do we do it to? To the virtual RAM, virtual memory. And virtual memory is a borrowed memory from where? From the secondary storage. Now there's another problem. RAM is very fast compared to the secondary storage. So now there's going to be a bottleneck, right? Virtual memory is going to be slower than RAM. So obviously there will be a performance, loss. I mean, lack of performance. That will be especially if your secondary storage is hard disk drive. So to reduce that performance issue, what do you do is, I mean, how can you reduce that? By having a SSD. If your secondary storage is SSD, there won't be much of an issue because SSD uses flash memory and it is about 100 times faster than HDD. So there won't be much of a difference of the speed.
Yeah.
Understand, all of you? Can I see a
Yes,
thumbs
sir.
up?
Yes, sir.
Thumbs up or thumbs down? Can I see thumbs up, thumbs down? Perfect. Who's Rukshana? Rukshana, what is your... I haven't heard your name now.
Sir, I'm Mida.
Oh, Mida, right. Okay, right. Okay, see, you might notice that this has a lot of disk activity. Your computer might run more slowly when a lot of applications are open. So one thing you can do to solve this problem is use an SSD or simply increase your RAM. Right? So modern computers, I don't think we need this virtual memory because we have plenty of RAM in our computers, right? But the applications that we run are also using a lot of RAM. So we might need this VM, the amount is controlled by the OS, but if you want, you can also set it. As well as the applications you are running, the operating system is also running. Remember, even the OS is running in the RAM. Everything is running in the RAM. And you know how to check that, right? You press Control or Delete, and then you go to Task Manager. And there okay, right. So when you go to the Task Manager, you can see all the resources and the processes running in the foreground and the background, everything. And you can see the resources allocated, CPU time allocated for this. Memory is the RAM, disk as well. GPU, if you're having a separate graphic card, you will have a GPU, right? Actually, not only separate, even internal, right? This internal, but one will be running at a time. So you will have a dedicated processor for running graphics. That's the GPU. Now see, even the CPU is fully used. And if not for GPU, I mean, GPU is anyway needed, but having a separate GPU will definitely be an advantage here. Especially in today's applications, right? Where most of the applications use a lot of graphics. So what they have done is they have given that job to a separate processor called GPU, graphics processing unit. Okay, so those are the process running. Some are running in the background, some are running in the foreground. They include various parts of the operating system. So even the operating system is running in the RAM. So the first thing what happens when you the first thing that happens when you switch the computer on is to bring the operating system from the hard drive and load it into the RAM, which is done by the ROM applications like the BIOS, Power on Self-Test, right, and the Bootstrap. These ROM applications, they bring the operating system. Is actually the Bootstrap which is responsible for finding the operating system from the hard drive and bring it into the RAM. This whole process is called boot up. So the operating system starts running in the RAM first, and then only the other applications. The scheduler, they include various parts of the operating system itself, such as programs that manage the network, the scheduler, also the hardware drivers, utility programs. All these will be running in RAM. Each task that is running is called a process. There you go. When a program is running, it's called a process, right? To see all the processes running, you can go to Task Manager, right? So update your book. Okay, so in Windows, of course, you can go to Task Manager. Linux, you have to type a command. In OS X activity monitor. And when you go to Task Manager, what are the things that you can see? What you just saw. The proportion of the CPU time spent on this process. That's what you saw, the CPU percentage. The amount of memory, that is the amount of RAM used by the process. Also, let me show you this. Now the program is running. It's a process, and it is holding into a certain amount of RAM. When you terminate the process, like let's say, okay, edge, how do you terminate the process? You just select it and press delete. That will terminate the process, stop the process. That amount of RAM it was holding will be released back to the RAM because it's a resource, right? So how do you terminate? Just select it, press delete. It will be terminated. Then we also call it killing the process. The amount of available memory, real memory and virtual memory, VM. All these resources can be checked. These processes are running one at a time. Okay, here's another job of OS, right? These processes are running one at a time, being given their share of the CPU by the scheduler. So scheduler is a program which is in the OS, and its job is to allocate the CPU time for different processes in a time sharing basis. That means up to certain time, certain extent, it will give the CPU time to one process and then switch to another process and then later come back. This is called scheduling. They are all running alongside one another, but not really at the same time. So we say they are running concurrently. Well, if it is concurrent, of course, they must be running at the same time, right? But if you have a single core CPU, it will create an illusion of concurrent running, right? It will make sure the CPU switches really fast among the processors. So for us, we feel like all these are running at the same time. So they're actually talking about a single core processor, right? We have opened so many applications. We can switch among them really fast, but they're actually running one at a time. CPU is switched really fast among these processes. Therefore, we feel that these are running concurrently. So it's an illusion. Okay, it's an illusion. But nowadays, of course, we have CPUs that are having multiple cores, multi-cores, dual core, octa-core, hexa-core, quad-core. So they, of course, they can have true parallel processing. When one core is handling one process, the other one can handle another. But if there's only a single core, that has to switch really fast among the process. It happens so fast that we feel that we are running these applications at the same time, concurrently. An operating system that allows processes to run concurrently is called a multitasking operating system. Because of this concurrent access, concurrent running. For us, what's the advantage? Advantage is multitasking. When we started computing back in year 1998, right? 1998, we didn't have concurrent access. We had systems where we had to load one program, work on it, close it, and then open the other program. Can you believe, right? There was no such thing like copying some data from one application to another application. That was like we hadn't even thought about it. We just had to open. There was no Microsoft Word. There was like software like Word Perfect. We had to open Word Perfect, type the letter, and then close it to open the Excel application. And it was not Excel. It was called, what I used was Lotus 123. So one application at a time, no concurrent access. But with this concurrent access, where the CPU can be scheduled among processes, users are able to do multitasking. So the operating system has another job, another function. What is it? It is the multitasking. So the operating system does multitasking. Okay. As well as allowing multitasking, some operating systems allow different users to use hardware. In some cases, only one user can use the hardware. So we call it a single user. In others, several users can be sharing the hardware, and that is called multi-user systems. Multi-user. Your smartphone is an example of a single-use system, while your school network servers will be running multi-user operating system. In our school, the server is running on Windows Server, which is a multi-user operating system, and it is able to control the whole network. This is so that many of you can log at the same time. A multi-user system, each user has to identify themselves. How do they identify? Using the username and password. When they identify using the username and password, it is called authentication. Authentication. Authority to use the facilities of the computer system is based on what you are. Right. Okay. So here's another job of the operating system. What is it? It can authenticate users. Right. So you are seeing a lot of jobs or functions of operating system, but it's all in this paragraph. Right. Authentication server. Okay. There is usually also a super user. Right. Now, when there are now it's a multi-user system, so there'll be a lot of users, and there'll be user levels also, like the restricted user, the super user. Super user has more privileges, right? It can be called the administrator also. Administrator has all the privileges in the network, whereas restricted users, students, teachers, they have different privileges, right? So how can you give different privileges to these accounts? By something called access rights. Access rights. Okay, here's another job of the operating system. What does it do? It allows us to set access rights. Okay, you highlight this, set access rights. Access rights are also called permissions. Permissions. Right, these include read, write, execute. Read permission, write permission, and execute permission. This is where some people are allowed to open the file and edit. Some people are allowed to read only, right? Access rights. So operating system sets access rights. Finally, the operating system also provides and runs the user interface. Sometimes this interface can be a graphical user interface. It can be a menu-driven interface. It can be a command line interface. If it is a graphical user interface, okay, one student is joining right now, and the class is over. Okay, so if it is a graphical user interface, you would have WIMP components. What do they stand for? Windows, icons, menus, and pointers. Okay. Right. Any questions, any doubts? Now you have a job. What you have to do is you have to list down all the functions of an operating system. Right. So this is homework. List down all functions in all functions of the operating system mentioned in these paragraphs. Okay, so they haven't listed these functions. They have given it inside these paragraphs. So when you're studying, make sure that you list down all these functions. Right? Now, apart from what you have learned for IT, today you learned about the scheduler. Okay, let's do a quick recap, right? Yeah, that's the end of that section. You learned some important concepts. You learned about the scheduler, scheduling, time sharing, controlling two important resources, CPU time and RAM. And then when the RAM runs out, virtual memory, use of virtual memory, swapping in and out or paging, which is handled by the operating system. And we talked about interface. We talked about running applications concurrently by switching the CPU time really fast. And as a result, we could enjoy what is known as multitasking. What enables multitasking is multi-programming, which is actually the scheduling of CPU really fast. Multi-programming, because of operating systems multi-programming, we are able to use multitasking. Then we talked about controlling input and output devices. We talked about providing an API so that other developers can write programs to run on a particular operating system, right? Because the API has some common functions, commands that other people can use to talk to this OS. And we also saw the OS is an interface between the users and the hardware. We also saw that OS can authenticate users, and some OSs can handle multi-user systems like the OS running on servers, multi-user operating systems. Then we have single-user operating systems running on personal devices. What else we learned? They provide user interfaces, different types of user interfaces, GUI, command-driven, and menu-driven. The choice of user interfaces depend on the application of the computer is expected to run. An embedded system might not have an operating system. There you go. Embedded systems, they don't have an operating system. They just run or execute the instructions. Therefore, it does not have a user interface, or the user interface will be minimal, like usually a menu-driven interface. A computer acting as a web server might only need a command line interface because it is intended to only ever to be managed by technicians. So where there's more security needed, like on servers, they use command line interface. Why? The operator has to know the command, right? Client computers will definitely have GUI because there should be more intuition, user friendliness. Embedded devices will definitely have a menu driven interface because we must be able to select the options, where we can't use WIMP in there, and you can't ask the users to type the command. So it's easy if we give them the chance to select the command. The computer used for video editing should all definitely be a graphical user interface. Now you can see there are different interfaces and there are different applications of these interfaces. Okay, so that's it. That's the first part of this. We need to complete this. Where are we? 190. 190, I think we have to do up to, oh, just 3 more pages. 193. 91, 92, and 93. Yes, we're almost done with software. So in the next class, we can finish this. And then we have the last chapter, which is, last theory chapter, hardware. Then we need to do this. We need to do, we are done with software almost, and then we have to complete the hardware, but only up to virtual memory. So that's also little. And then we did strings. We need to do input, output, and testing evaluation. That's all. Right? Any questions? Any doubts? Any problems?
Sir, can you upload some past papers?
Yeah, I can do that. I actually yeah, I will certainly do that, but I'll be doing papers with you. I'll be doing papers.
Okay, sir.
Because even if you do it on your own, it's important that you give it to a teacher and get it corrected. So I'll be doing the past papers. I will actually I shared the past paper today with Tusharika, man. She wanted some papers, but I'll be doing. Certainly I'll be doing. And after this week, of course, I'll be having some private classes. I'll be starting private classes until I leave, and they also I'll be doing papers, and then I'll be trying to cover the most of the syllabus before I leave. By the way, I heard some are going to drop computer science. Is that true? Some are going to change the subject, it seems. Tusharika ma'am told me. I don't know whether it's you guys or the other guys. Right. Okay. So that's our plan. Nah? Software is almost done. Then we finish hardware. And then we have input output. And then we have testing and evaluation, which is a practical part. And then we'll be doing papers. So I'll be I'm trying to finish everything within this week. So that next week onwards we can do papers. Okay. In the meantime, I will share a few papers also, right? Okay then. See you. Good night.
Thank you,
Okay, good
sir.
night, sir.
Good night, sir.